In this lesson, we're looking at equipotential lines, and here are the objectives. Let's start with a large positive charge. I've drawn in the field lines already. We know that the field lines point outwards from a positive charge because they indicate the direction of force on a second positive charge. And if the central charge were negative, then the field lines would point in towards it because a small positive test charge would be attracted in towards the negative charge. Now let's think about the potential. This is showing the field. Remember that we define potential as the potential energy per unit charge, per coulomb in this case, to bring a small positive test charge from infinity to a given location. So, for example, if I look at this location right here, and I say that that is at a potential of 60 volts, it means that it takes 60 joules per coulomb to bring a small positive test charge there. And because of the radial symmetry here, I have points like that all the way around. So this dotted line is connecting points at 60 volts. And so we call this an equipotential because it is connecting points at the same potential. If I go out by another 20 volts, let's say I go to here, and all the points along this circle are at positive 40 volts. And if I go out by another 20 volts, I have to go further. So the equipotentials get spaced out further as I go away from the central positive charge. And this would be at positive 20 volts, let's say. So 20 joules per coulomb to bring a small positive test charge to this point, or any point on this circle, from infinity. In contrast, if I look at the negative charge, it takes negative work to bring a small positive test charge here. So this could be, for example, at negative 60 volts, and then going outwards at negative 40 volts, and going out further at negative 20 volts. These two charges are meant to be separate pictures. They're not part of the same picture. So just imagine a separation here. And there's another separation here because in a moment we're going to look at the gravitational situation. First though, let's look at a simulation of the electric situation. We can see here that we have a central positive charge. It's at 5 nanocoulombs, and this charge I've reduced to 0 nanocoulombs, so it's not even there. Central positive charge, and we can see the equipotentials going out around it. Note that the equipotentials, as we've said, get further spaced out as we go away from the central positive charge. We also have this sensor that's measuring potential, that's V, and we can see that that goes up as we get closer to the central positive charge. It's also measuring the electric field strength here in newtons per coulomb, and that's also indicated by the length of this vector arrow. Again, notice that the electric field strength goes up, the arrow gets longer as we get closer to the central positive charge. Now, if I change to this three-dimensional view, you can see that, again, as we've said in earlier lessons, height is a good analogy for potential. As we get closer and closer to the central positive charge, we move to higher and higher potentials, and that's shown here by higher and higher heights. If I go back to here, you can see what that's doing. So this is like a topographical map. Also notice that where the equipotentials are bunched closer together, the field strength is stronger. This vector arrow is longer. And that corresponds to a steeper slope, again, if we're thinking about the potentials as height. I can also change this to make that central charge negative. Notice now that the vector arrow for the electric field points in the opposite direction, and my potentials are now negative. If I go back to the three-dimensional view, you can see that now, instead of a little mountain, we have a pit, indicating that potential gets more negative as we get close to the central charge. Again, height being a good analogy for potential. And that might help you see that the gravity situation is analogous to the negative central charge situation. We have a mass in the center, the field lines point inwards because gravity is always attractive, and we have equipotentials that are concentric circles that get spaced further out as we go out from the large central mass, forming that kind of pit or well that we just saw for the electric situation. Now in this case, we can't measure in volts, we're measuring in joules per kilogram. So this could be at, let's say, negative 20 joules per kilogram, and this could be negative 40 joules per kilogram, and negative 60 joules per kilogram. So notice that the equipotential lines and the field lines are always perpendicular to each other. Equipotential lines are always perpendicular to field lines in all of these cases. Also remember from how we define potential that the change in potential energy in the electric situation, let's say, per unit charge is equal to the work done by the external force per unit charge, and we called that the change in electric potential. From that then, we can see that rearranging this equation, the work is equal to the charge moved times the potential difference through which you move it. Or analogously, in the gravitational situation, it's equal to the mass times the potential difference through which you move it. So for example, if I wanted to go from negative 40 joules per kilogram to negative 20 joules per kilogram with a 3 kilogram mass, so I'm taking a 3 kilogram mass and I'm moving it from here to here, the potential difference through which I'm moving it, final minus initial, is positive 20, because I have negative 20 joules per kilogram minus negative 40 joules per kilogram. That's my potential difference, and that's equal to positive 20 joules per kilogram. And so I have to multiply that by my mass, which is 3, and I get a total of 60 joules of work being done to move that 3 kilogram mass from here to here. Also notice that that implies that it takes no work to move along an equipotential, because if the change in potential is 0, then the product here is 0, the work is 0. So moving this 3 kilogram mass anywhere along this equipotential would take no work. Again, think of the height situation. You're not changing your gravitational potential energy if you're not changing height. And so you don't have to do any work against the gravitational force. Now let's look a bit more at a charged sphere and the electric potential inside and outside a charged sphere. So I'm going to draw a positive charged sphere here. And imagine that there are a bunch of positive charges distributed around the surface of this metal sphere. And because it's a metal sphere, a conductor, the charges are going to mutually repel and spread out as far apart as possible. Now I'm going to graph the potential as a function of the distance from the center of the sphere, r. So here, let's mark off where the radius of the sphere is. We'll call that our sphere. So that's the dividing line between inside and outside the sphere. Now we know from our equations in a previous lesson that the electric potential outside the sphere follows this formula. In other words, outside of the sphere, the electric potential is proportional to 1 over r, the distance from the center. And so it's going to look like a reciprocal graph like this. Now inside the sphere, it turns out that the potential is constant, so it's just a straight horizontal line. So this is outside the sphere. Inside the sphere, the potential is constant. In other words, if the surface of the sphere is at, let's say, plus 100 volts, then so is everywhere inside the sphere. And if I were to put a charge somewhere inside this hollow sphere, it would have the same potential energy per unit charge no matter where I put it, and it would take no work at all to move it around inside the sphere. As we'll see in the next lesson, this constant potential inside the sphere also implies that the field strength inside the sphere is 0. And this is actually why it's a good idea to stay inside your car if you're caught in a lightning storm, because the charges from the lightning, if it strikes your car, will distribute evenly around the car, and there will be no electric field inside the car, and so you won't feel any electric forces. So above we were looking at situations where the field lines radiated outwards. Now let's look at uniform fields where we have parallel field lines. So here on the left, this is our parallel plate capacitor again, and our field lines are going to be parallel, and they're going to point downwards in the direction that a positive charge would feel a force. And in this case now, because the field is uniform, our equipotentials are also going to be equally spaced, and they're going to be perpendicular once again to the field lines. So now let's say our negative plate we set at 0 volts and our top plate we set at plus 100 volts. Then this would be our 25 volt, 50 volt, and 75 volt equipotentials. And as we've seen earlier in the gravitational situation, to get a uniform field, we need to get close to the surface of a massive body like the Earth. And now our gravitational field lines are parallel and pointing downwards towards the Earth, and our equipotentials are once again going to be perpendicular to the field lines, and they're going to be evenly spaced because the field is uniform. So this could be, let's say, 25 joules per kilogram, and 50 joules per kilogram, and 75 joules per kilogram equipotential lines. And this down here is our reference point at 0 joules per kilogram. So that's a look at equipotential lines within electric and gravitational fields.